This material and energy balances video is a summary and wrap-up of Chapter 4, Fundamentals of Material Balances. Some of you may be very happy to hear that we are finished with Chapter 4, moving on to something else, but I have to caution you that fundamentals of material balances are something that you are never truly finished with as a chemical engineer. At the very beginning of the class, when I said this was a checkpoint class and that you would have to master material balances in order to even be competent in anything else, this is exactly what I was talking about. So even if the first exam didn't go very well, a question that you may have is, are the upcoming exams going to be cumulative? Or do you have to, are you going to be tested on stuff from Chapter 4 in the future? And while the answer to that question is technically no, I have to share that the material of Chapter 4 is the fundamentals for everything else. So while we'll move on to other stuff, that stuff will assume that you have already mastered the fundamentals of material balances, because in the rest of the class, we'll just continue to add complexity and more stuff to the skeleton of what we've already started to learn. You notice I have my copy of the textbook up, and that was because I wanted to briefly touch on everything that we'd covered so far, and also highlight some things that I didn't explicitly talk about in class, but I'll still recommend that you look at for yourself. And while performing the homework assignments, you may have noticed that you may have had to look these things up yourself already. The first is that of process classification. Remember at the very beginning of this chapter, I talked about the three ways that you could classify a process. And the first classification that you can make is that of batch, continuous, or semi-batch. So we've talked explicitly about continuous processes. And we'll continue to talk almost exclusively about continuous processes. Only in the very end of the class will we talk about batch processes. And that's because mostly everything that's made at scale, with a couple of notable exceptions like pharmaceuticals, are made at the continuous regime. So there are some batch processes and even some semi-batch processes, but I'd say a majority of the processes that you'll see in chemical engineering are going to be continuous. And that is why we've done material balances all on continuous processes. The only thing that changes for batch reactions or batch processes is that there's no inputs and outputs, so you almost always have a chemical reaction inside in order for anything interesting to be happening. So once again, in section 4.2b, we talked about how to balance a continuous steady state process, and that's almost exclusively what we've been doing. I did not cover section 4.2c yet. This is integral balances on batch processes, but we'll come back to this at the very end of the semester when we talk about unsteady state processes. Then 4.3a is the heart and soul of this class, material balance calculations. Look at the flow charts. I love this sentence in this book and in the years to come. So once again, not just in this class, but in every class henceforth, a material balance is going to be at the exact heart of everything else that you do. So this is why it's so important for me to make sure that you know how to do a material balance, because without being able to do a proper material balance, your chances of being able to do anything else in chemical engineering are small. I've skipped ahead a little bit, but I wanted to explicitly talk about this section. One of my favorite sections in this textbook is 4.3f, which talks about, in textbooks, a balance will usually close, but in real chemical processes, not so much. The reason why I love this section is because it really compares and contrasts and reconciles what we do in class versus what you would do in the real world. So while it's true that you would never solve a material balance problem in exactly the same way in real life, it's important to know the fundamentals of how material balances work. And this section of the textbook talks about how chemical processes are different from what you would actually see in the textbook. So it gives this example of a mixer. And in every problem that we've had so far, there's been a couple of unknown variables. Whereas in a real process, there's no reason why you wouldn't know every single variable in the process. You'd be able to measure temperature, you'd be able to measure pressure, you'd be able to measure these flow rates and measure these compositions. But a material balance is a great way to double check that your equipment is functioning properly. In other words, if your material balance doesn't close with all given information, and the way I think about it is if the information that your process units give you is contradictory, then that's going to be an indication that something isn't quite working properly. So it's unfortunate that I can't cover this in a problem. So like there's no way that I can really test you on this material. But once again, I really encourage you to read this section of the textbook, because this is the type of stuff that will prepare you for being a, quote, real world engineer. So it's not a very long section, but again, one of my absolute favorites. There's another section at the end of the chapter that I'll talk about briefly. So before I move on, I also wanted to cover some things really quickly that I did not cover that are in Chapter 4. Chapter 4, like I said, is the most important chapter, but there's not enough time to cover everything in detail in this class. The first is the concept of chemical equilibrium. So this will be something that you revisit in your kinetics class and possibly in your phase equilibrium class. But for material balances, we're going to assume that all reactions are irreversible, or it is only proceeding in a single direction. And this is what I mean by MEB is oftentimes seen as, quote, easy by the upper class students because of all these simplifying assumptions that we make. So if you notice that in all the problems that I'm giving you so far, we've only assumed an irreversible reaction, but you can also have a reversible reaction happening where the reaction can proceed in either way. So don't worry about this too much. This is just a preview of things that are to come in your chemical engineering curriculum. Section 4.7b is important because it introduces the concept of independent equations. So remember, for an extent of reaction analysis, when you're doing the degree of freedom analysis, you have to count the number of independent chemical equations as unknowns because each one of them has a corresponding extent of reaction. I think I got this question in class of what does an independent set of equations look like? And if that's a question that you have, I encourage you to read this section because it illustrates what it could potentially look like. So in this example, equations 1 and equation 2 are not independent simply because the second chemical reaction or equation is multiplied by 3. And the same thing can happen with chemical reactions. So if a chemical reaction is just simply multiplied or combined in some algebraic manner, then it doesn't count as an independent chemical reaction. Some other things I didn't talk about that are going to be useful as you solve problems. This number, this ratio of N2 to O2. So there's two ways that you can, if your flowchart specifies air, you can either say that air is 79% N2, 21% O2, or you can say there's 3.76 moles of N2 per mole of O2. And this is the number that you get if you divide 0.79 by 0.21. So you want to memorize both of those numbers. And again, whenever you see air, because for a reactive chemical balance, it's useful to draw your process flow chart like this in terms of overall amounts of each component rather than overall amount and composition. So having this as a process specification will be quite useful. Concepts of overall conversion and single pass conversion are covered in section 4.7f. So we saw those in a recent problem. Again, you'll want to go back and read the textbook. Whenever there's a term that is unfamiliar, you can either look in the index of the textbook or you can just do a Google search on it so that you can find some information about it. That's also a skill that is useful for lifelong learning, is whenever you find an unfamiliar term, just do a quick Google search on it and see what you can find. Some of these things I intentionally have not covered in class only because they're simple definitions, and I don't think that just reading you the definition and telling you is teaching you. Sometimes you have to learn how to find things on your own. So hopefully you've seen these in your readings already. Purging is another topic that is going to be important, but that I haven't explicitly talked about. A purge stream is basically an exit of the process such that things are not accumulating. So if you have something going into your process, it has to have a way to get out of the process. Otherwise, it is going to accumulate. Or it could also be consumed too. That's another possibility. And then finally, in the combustion section, combustion chemistry, they define the terms wet basis and dry basis, stat gas, flue gas. These are all terms that you may see in a future problem. And when you see them, you should know where to find them. So somewhere in chapter 4. Once again, if you look in the index of this textbook, or if you simply Google it, you should be able to find the information that you need. All right, I'm finally wrapping up. Section 4.9 is my other favorite section of this textbook because it just gives you some additional things to think about that you cannot really test or show in a regular textbook problem. So certain things like textbook processes are always designed, or they always work how you think they're going to work. But in practice, things don't work as common. In the unit ops lab, students are always telling me that equipment breaks all the time, doesn't work how it's supposed to. And sometimes your job as the engineer is to figure out why. But in order to know why, or to posit a reason why, You have to know how it's supposed to work in the first place. And that's how these types of analyses can really be useful. This is another one of my favorites. In textbooks, you always have exactly the data you need to determine what you want to know. But in practice, you may have everything that you need, or you may have absolutely nothing. So you have to figure out how to deal with that problem in real life when you have positive or negative degrees of freedom. Related to that idea is that textbook problems having one and only one correct answer, and you're just following a cookbook recipe in order to determine what that right answer is. In real life engineering, sometimes you may not know what the problem is in the first place. And once again, that is a skill that is very hard to teach. We do our best in trying to teach you this in engineering school, but be aware of that is one way that real world engineering differs from classroom engineering. And if classroom engineering, you're finding difficulty with it, just know that there's hope for you because real life engineering is different in some ways. And that will wrap up this video. We bring chapter 4 to a close. It's sad because chapter 4 is my personal favorite chapter of any section of any chemical engineering course. But like I said, chapter 4 is something that's gone but never really forgotten because it will continue to be at the forefront of everything from here on out. And if there's anything in chapter 4 that you did not understand or that you think you could get better at or improve with, now is the time to go back and make sure that you're perfecting these techniques. Because like I said, it'll only get more harder and more complex as we go on. So that'll be all for this video. In the next couple of videos, we're going to cover chapter 5.